welcome to the third class for Cert for Materials and Methods, and also welcome to the other internal class who's watching this video today. So with this class, we got to grab that. So we got part way through the timber framing last week. We got down to coupled and non-coupled grooves. That's correct? That's where we got to last week. So, did you want to have a quick refresher through what we went through last week, or just get going? Okay. So we covered timber framing, the extents of the timber framing code, all of our terminology. So ridge, batten, hanging beams, ceiling battens, first floor wall frames, external cladding, ceiling, rafter, roofing, etc. The way through the limitations of the timber framing code. So maximum wall heights, imposed loads on the building, wind speeds N1, N2, N3, and N4, and the basic terminology, roof framing, wall framing, and floor framing. So you build from the bottom up, but you design from the top down, because the roof loads imposed upon the frame dictate what the frame imposes upon the floor, which dictates what the floor imposes upon the footings. We have to be sure that we have continuous paths of load, that we don't have too much eccentricity in forces. Looking at the way loads distributed equally between members. However, when we have a continuous span, we have a differentiation of load imposed if the spacings of the supports are unequal. We distinguish between span, single span, continuous span. And rafter span is measured along the length of the rafter, not the distance in a horizontal fashion from ridge to wall frame. The spacing differs from span in that the spacings are measured from centre of the members to centre of the members. Differentiated between load-bearing wall and non-load-bearing wall. And we've arrived at coupled grooves. So a coupled groove is whereby we have the rafters joined together, stopped from spreading by a ceiling joist and or column tie. What we have here, it says this method of construction is not covered by Australian Standard 1684, where we simply have a collar tie joining the two rafters. So what's covered by 1684 is both the ceiling joist and collar tie further right. But if we have neither of those, gravity loads imposed on the roof will cause the tendency of those rafters to spread and push outwardly on the wall frames. And if there's nothing to stop the wall frames from spreading, the wall frames can tip over. The way that this was done in a lot of traditional buildings, your old churches, etc., that have the really high ceilings, is by what are called flying buttresses on the outside, which are large walls that lean against the main wall and stop those from falling out of it. Quickly, can everybody think what a flying buttress is? Or should I quickly draw that up?
You've got the wall and it's sort of like brickwork, maybe up to about 1.2 or something.
Yeah, exactly. Yeah, so that's a buttress, and then flying buttress is much the same, except that flying buttress that's where I guess typically it's just a bit more ornate, but it takes materials out from where they're not needed. So your standard buttress is like that on your church, and then your flying buttress, you'll see, misses that amount of material in there. Have you ever seen that on buildings? So it's basically just once again the introduction of an arch. So because we don't actually need this material in here, and then we curve that like that as well. So yeah, just a little bit of trivia. But that's how they stopped their wall frames from spreading and rotating under load of the roof when the roof wanted to push the walls out. Of course, we don't really want to go adding buttresses and flying buttresses to our standard dwellings. So we tie the roofs together with ceiling joists and collar ties. Another way of stopping that spreading is to support the rafters in an intermediate fashion. So back up to our church up here, we can have a large beam in the centre that runs from this wall through to the rear wall that supports those rafters. So as we can see on the slide here, a beam that runs all the way through the building that supports those rafters to stop them spreading. And of course, this requires a very large beam because it has to make a very large span. It depends on the run of the building. And then also, to minimise the depth of the rafters, you can provide an intermediate beam doing the same thing. That's right. Through there. So roof framing. The footprint of a building generally consists of a rectangular block or multiple blocks joined together. So the vast majority of houses, you can break it up into a series of blocks, and that's where we derive our roof shape from. So if we start, let's go to this one here, the top left hand. We've got just a simple rectangular building, which lends itself to an equal hip roof, a gable end roof, or a skillion roof, either way. Or we could do a Dutch gable. When we start adding articulation to that floor plan, or some re-entered corners, then we need to think about how we roof over that articulated space. So that dictates what our roof will look like. I'll just quickly sketch up something like that as well. Do it over here. So let's say we've got a floor plan. Actually, I'll make this wing slightly shorter. Just do it very simply. Get a floor plan like that. We want to do a gable end, a hip end on that. So the hips go through there. Our hip will run from there. We'll do a minor hip here. So that's our major hip and our minor hip. But where this one intersects, because this roof is lower, so that's running through to there. Got to do all the right angles. This intersects with that, like that, and then we have a valley in there. And then we can make that, as complex as we wish. If we want to add another wing of building out there and hit that roof, that one joins in at a point there, for example, and we create a valley in there. So our floor plan, the shape of our floor plan will dictate what our roof is doing. So some more terminology again, a bit of a refresher. So our ridge board right at the top, our collar tie maximum 2/3 way up the rafter run. Got an underpurlin supporting rafters running from ridge through to fascia. Well, this building doesn't have a fascia. show a fascia at the end of the rafters. We've got a top plate on top of our wall studs, and then a strut to strut our underpillar. So a vertical strut and a perpendicular strut to our underpillar. And then, of course, a load-bearing wall here as it's picking up that strut there. This strut's not carried by a load-bearing wall, so we've got a strutting beam picking that strut up. Transferring the loads. Roofing material takes live, dead and wind loads and transfers them to the battens. Battens take roof loads and transfer them to the rafters or the trusses. Rafters take batten loads and transfer them to the support structure below, so to the walls. Process, step 1, determine the wind classification to factor in wind loads. So assume non-cyclonic winds N1 or N2. Determine type of roof, is it tile or sheet? Determine batten spacing. So typically 330mm for tiles, or for sheets, what says 450, 600, 900, 1200. Yeah, so your typical spacings for sheets, well, it's hard to say typical, but they're the 900, 1200, or even greater for some of your decking materials. Determine batten span. This will be the supporting rafter spacing. So go to roof battens. Let's say we're doing a tile roof, so our battens at 330 centres. 25 by 38. What do we got here? Oh yeah. So unseasoned hardwood. So F8. So it's fairly typical that your tile battens are hardwood battens. You don't use softwood for your tile battens. So it's the right table. Although it's good to use seasoned hardwood. But we've got table for unseasoned hardwood here. So if we're going to have our rafters at 600 centres, we're going to have to use the 25 by 75 battens to achieve that span. However, if we've got a gable overhang of more than 250mm, then we have to up the size of our battens to make that gable overhang happen as well. So just the client's choice of gable overhang of a 600 overhang on the gable will mean that the battens have to be boosted up to 50 by 50. So wind classification in 1 and 2, choose a table reflecting preferred stress grade. Here they've chosen sheet, so raft spacing 1200 and 1200 by 75. So the process of batten choice again. Well, I think we'll flick through this fairly quickly. So wind classification N1, N2, stress grade F8, batten spacing 900mm. We want span 900. So we've got 38 by 75. The selection of timber from span tables, that's all fairly straightforward to you guys. Is it from that? So determine the wind classification to factor in wind loads, for example. I think we're going through much the same thing again. Determine dead live loads on rafters. For this example, assume loads are as tile roof with battens. So 60 kilograms per square metre. Determine the rafter span. For the example, assume 2100mm rafter span. Determine the rafter overhang, which creates a cantilever span, adding extra load. For example, assume a 500mm overhang. So that might be our killer. We'll see that when we get to the span table. Determine the rafter spacing, as this determines how much roof loads are shared between rafters. For example, assume a 600mm spacing. So our rafter spacing of 600mm. So we start with our wing classification and choose our seasoned softwood and our stress grade. Now you don't always do that in that fashion. You don't always go, well, typically you do, like for when you know much of your timber is going to be M&Mc4, you just go straight to the M&Mc4 table for specifying your timber. But with battens or with specialty timbers, you may not decide this is the stress grade I want. You may go through this process and go, oh look, I have to use fairly large members with that stress grade. I'm going to look at another stress grade which is not too much more expensive and go that other option. So it's not always choosing the stress grade first. So here we have raft spacing at 600 centres. To achieve our overhang of 500 millimetres, we've got to go with a roof load of roof and ceiling mass of 60 kilograms. We've got to go with a 90 by 45. Well, 90 by 45 will allow that roof mass with this overhang at that raft spacing. So I think we get the gist of the stand table style. So I'll just flick through those for now. So design variables: timber stress grade, ceiling joist spacing, ceiling joist span, single or continuous span. And we may decide with this ceiling. So once we go through the process, we arrive at 120 by 45s. But that's not a massive or unusual size of timber, so we'd probably leave it at that. Or we may go back to the drawing board. Let's go back through. We may decide, well, it's possible to put in a hanging beam here in the centre, and then cut our ceiling joists down to 90 by 45s in the process. So 90 by 45, we've got N1, N2, F17, stress grading, joist, what is that joist spacing? Joist spacing of 450, so we're looking at this table here. So that will allow a single span of 2600. So yeah, so halving it with a hanging beam from our, so we had, was it 170 45s, enable 5600 span. If you halve that, we can, with a hanging beam, we can knock it down to 90 by 45 joists for the ceiling. So some members do not have to be designed using span tables. They are simply called up or calculated based on members framing into them. So for ridge board, the size of the ridge board is depth not less than the length of the raft of plumb cut by 19 millimetres thick. Hip rafters, 50 millimetre greater in depth than rafters by 19 thick or 20, 25 thick. It's unseasoned. That's so same for valley rafters, etc. etc. Roof struts up to 1500 millimetres long for all stress grades, 90 by 45 or 70 by 70, and struts longer than 1500 millimetres but not longer than 2400 mil, 70 by 70. So within the timber framing code, they prescribe simply the sizes of some pieces of timber that are not prescribed in the design tables. So the loads from the roof members often impact on the design of members lower down in the structure. This impact can be determined from the following load sharing calculations. So we start with roof load width, ceiling load width, and roof area supported. Roof load width is the width of roof that contributes roof load to a supporting member. It is used as input to span tables for floor bearers, wall studs, lintels, ridge or intermediate beams, veranda beams. The roof load widths are measured on the break of the roof. So the load going to going to point A here, for this very simple span, is half that distance. So 1500 millimeters is the roof load width acting on that. Here's some other more complex scenarios. So roof load width acting upon B, for example here, is Y, so that direction, so from the ridge all the way to the top plate, plus the eaves overhang, because we have no other point of support here at all. So, and that's the same for the load on A. It's half of that roof. And the roof loads of trusses are distributed equally between walls A and B. So that's what we saw in that last diagram. For a pitched roof without ridge strut, it is assumed that some of the load from the unsupported ridge will travel down the rafter to walls A and B. The roof load widths for walls A and B are increased accordingly. So our roof load width for A and B includes up to our first underpurlin here, plus our length of B. So our underpurlin number 1 is carrying half the load, or the load from the distance halfway between point A and number 1, and then half this distance once again. This strut, or that ridge, is taking half that load. Underpurlin 2. Well, it says y divided by 3. Yeah, okay, because they're equidistant spaced. So we can simply get this y distance and divide that by 3, or we can measure halfway between this area and halfway between this area, and we'll arrive at the same answer for that roof load width. So does that make sense, the calculation of roof load width in the various scenarios? I think that's fairly straightforward concept. And same for the ceiling load width. So we've got a hanging beam here. The hanging beam is not calculated as taking the whole ceiling load width. It shares that ceiling load width with this point of support and that point of support. Hence, the extents are calculated halfway between the hanging beam and the outside wall, or point of support A. So ceiling load width is used as an input for span tables for hanging beams, and strutting beams, or strutting hanging beams. Yeah, we'll just flick through this quickly because it's all very simple. So it's carries half the load between those points. When we get into roof area supported, once again the very similar concepts apply. So the strutting beam span table requires roof area supported square metres. The strutting beam shown supports a single strut that supports an underpurlin. The area required is the roof area supported by that strut. The way that we calculate the extent of that is with this underpurlin being located midway. Well, actually, even if it's not exactly midway, it carries half the width of the roof from top plate to ridge. So it's the same sort of calculation for roof load width supported, but you multiply that by half the distance between this strut and half the distance between that strut to that strut. So we end up getting a square or a rectangle of roof area supported like that. Is that fairly straightforward? So these same diagrams are in the timber framing code as well. So if ever you're going into tables and you think, oh, actually, how do I calculate roof area supported by a strut? You can flick to the front of the timber framing code, and it has these diagrams in there explaining that. So I think we've used timber framing the span tables enough. So get into wall framing. These are a bit more terminology. So metal bracing, strap bracing, typically your 30 by 0.8 galvanised iron strap, and yeah, it's called Type D bracing. We have our common stud here. They're separated by our noggins. We have a wall intersection here, and that's what we call a stud cluster. So it's where you have several studs together to create an intersection. And our jack studs underneath our lintel trimmer, and then the jam stud running up the side of the opening. We have our bottom plate, our top plate, our lintel supporting the roof loads over the opening, and then our sheet bracing. So our sheet bracing, if you remember from last week, will provide about 6 kilonewtons of restraint per linear metre, whereas your Type D bracing is only about 3 kilonewtons of restraint per linear metre. So for another exercise, we've got our parameters. Width classification of N2, stress grade M&Mc4class3. Are the studs notched? So typically we choose yes for notched studs because we don't know what plumbers and electricians are going to do on site. So that enables plumbers and electricians to notch studs for various different activities. So we choose yes for notched studs. Stud height 2400, rafter spacing, truss spacing 900mm, roof load width 5 metres, stud spacing 450, roof type sheet, like steel sheet, 20 kilograms per square metre. I don't know what really contributes to this or not, but it's a bit of an odd one in that I found in doing some retrospective framing stuff through New South Wales, they typically employ rafter spacings of 900 millimetres. We don't really do that in South Australia. We stick to either 600 for tile or 1200 for sheet. Whereas in New South Wales and possibly some other states, they employ 900 millimetres quite often. So that's just a bit of an anomaly. We don't do that so much in South Australia. And also another odd one, stud spacing of 450 millimetres. We don't typically vary from the 600mm stud spacing in South Australia either. We pretty much always 600mm stud spacing unless we're fixing waterproof, water-resistant sheeting for the bathroom, which requires 450mm stud spacings. So, N2 classification, MGP. Given that, actually, it's great. Given that information, can anybody determine what stud size we will end up using? See if you can work through the table for the example gives it.
120.
What's that?
2 at 120 by 35.
2 at 120 by 35. Well, these are our these are our sizes down here. Do you go through the example or? So we've got our so grid classification N2, our stress grade MGP10, stud spacing. Stud spacing at 4. So stud spacing at 450 millimeters. Our roof type sheet 20 kilograms per square meter. We don't have that. On the table. Got rafter truss spacing of 900. So we're dealing with this column here. Roof load width of 5 meters. So these are our roof load widths in here. So 70 by 35 at 2400 will allow 7. And stud height 2400. So that will allow us a 70 by 35 stud. All that, because that will allow a 7500 roof load width at 2400. MGP10, 3 millimeters, stud spacing, 450, sheet roof type, down to this column here. That one, that exceeds the 5 meters at 2400, we get 70 by 35 studs. But I'll keep moving through the span table stuff because you guys will cover this in your assessed timber framing classes in far more depth, and we'll go into that. But that's how it's done. Once again, floor framing, floor members. Yeah, no, we won't work through this. So that's about calculating the floor load width onto various different bearers, etc., and determining bearer spacing. But that's it's a tedious process for in the class. So that's the extent of that. Duck into roof framing. Just quickly, because a lot of this is revision. So, got top plate, rafter, ridgeboard, collar tie, underpellet, strut, etc. A pitch of less than 10 degrees will not have the triangulation required to be self-supporting. Roofs with pitches less than 10 degrees are generally constructed using graded purlins. Has anybody seen that on site before? The use of graded purlins, where you have so it's basically a way of creating a curved roof as well. If you want to impose, let's say, we've got a we want to create a curved roof like that, and we want to have a point of support here, for example. Point of support there. We can't go running. So one way of doing a curved roof is to have a whole heap of beams that run in this fashion here, like this, and we bend the roof over that. Another way of doing it is to do a fairly simple type truss, having lower purlin or purlins on flat there. Same purlin on edge there, deeper purlin there, once again, and then having drawn a curve all that well. Purlin on flat in that scenario. So it's a way It's a way of essentially introducing pitch or curve from a flat thing, and just like in that work example there, we can have just a flat rafter like that, and then have a tall purlin, shorter purlin, same purlin on flat, creates our pitch for our roof. So that's just the approach with graded purlins. That framing members of a cathedral roof. So we've got our ridge beam and our intermediate beam that help support our rafters. So there's no collar tie or ceiling joists in that, because we want to have a raked ceiling on the inside of that roof. In terms of applying to timber trusses, so this is your first introduction to the timber trusses. We have our top plate or top chords of our trusses. So the rafter portion of our roof trusses are called top chords. The ceiling joist component of your truss is called the bottom chord. Those chords are joined together with webs that act both as bracing and as struts in various different wind loadings, and they're tied onto the top chords and bottom chords by nail plates. Beyond that, the other terminology should be fairly familiar. Interesting thing about hanging beams, using the soldiers to hang your ceiling joists. Each alternate connection should be fixed to opposite sides of the hanging beam. So we can use pleats, or we can use, I forget what they're called, not triple grips, but they're just your steel ties, I forget the name of those specifically. The ceiling joists shall support ceiling loads only. Any platforms constructed in the roof space above a ceiling for the support of a storage water heater, feed tank, flushing system or light shall be designed for these loads. Supporting walls also need to be designed for these loads. So you have to take into consideration what sort of loads are going to be imposed in your roof space. Typically we don't include storage water heaters within the ceiling anymore. It's not so much an issue, but the inclusion of solar panels, etc. is. Hanging beams shall only support ceiling joists and the attached ceiling materials. Hanging beams are usually at right angles or maybe angled or placed off centre to ceiling joists and are located directly above them. If I've got a series of, I've got a room here like this, I've got a joist across it like that, and then I'll make that much shorter room for the purposes of this demonstration. So I've got a short room like that, and I've got a doorway happening here, and let's say a doorway happening there. Now, I want to run my hanging beam as close to that centre line as I can, but I've got this doorway happening here. What I'll do is I'll run the hanging beam from there straight to right next to that door there, but that will mean that all of my ceiling joists have to be sized up to be able to meet the largest span of any one of those ceiling joists there. I can't just go, alright, the average span is this, or my short span is that. Great, I can use 70 by 35. I have to look at which one is going to have the longest span and do all my ceiling joists to match that. A couple of reasons: you don't want the carpenters to be flicking between sizes of timber for ceiling joists. but then you don't want to be packing out underneath the hanging beam as well to accommodate different sizes of ceiling joists for that. So, but for that reason, typically hanging beams run at right angles to ceiling joists. Where the slope of a rafters is such that the depth of the hanging beam shall be reduced by more than 2/3 in order to avoid interference with roof cladding, provision shall be made for additional support incorporating a jack joist trimmer. So here we have our hanging beam there, but of course hanging beams intersect, or sometimes pitching beams intersect with the roof plane, and we need to cut them down. If we have to cut them down by more than 2/3, we help support that hanging beam by a piece of timber underneath, back to our first ceiling joist called a jack joist trimmer. Counterbeams may be provided to support hanging beams. End support of counterbeams shall be similar to that for hanging beams. So that's our counterbeam there, and it's been cut down. So do we have an example? No, we don't. So of how we end up supporting or helping to support that counterbeam. At intersections of hanging and counterbeams, hanging beam may be checked out over the counterbeam or butted up to the counterbeam. So that's about how that counterbeam interacts with the hanging beam. The hanging beams should be supported by 45 by 42 minimum ledges fixed at each side of the counterbeam with 5 3.05 diameter nails or 2 number 14 type 17 screws or other proprietary connectors such as joist hangers. So hanging beam checked out over the counterbeam or butted up to the counterbeam. So in this scenario, they're butted up to the counterbeam. So we've got our counterbeam here, and we've got our ledges under there. The other scenario that was mentioned where they're checked out, no, we don't have a diagram for it. That's just simply like this. It's counterbeam like that, hanging beam, butts up against it, but it's notched out to accommodate on top. Still use a ledger. If you don't use a ledger, you get a crack along there, like that. But in regards to to specifying all these fixings as well, typically as a drafter you don't specify, how do I say it, these, where you've got a scenario where it's just standard fixings, so it's specified in the timber framing code, this is how we fix a hanging beam. The drafter doesn't specify those on the plan. You say all timber work shall be constructed as per AS 1684. And then you'll say fixings as per table this in AS 1684, for example. So we don't go specifying all those fixings, and unless we're carpenters, we don't necessarily need to know them. Where we do specify fixings, though, when it comes to bracing. So if you're going to be specifying bracing, or tie downs, you'll specify this bracing, and it has 3 2.8 diameter nails at each end of that bracing, or it has 4, or it has 5, because that gives you different kilonewtons of restraint. Typically when specifying tie downs, we'll go, alright, a tie down, this galv strap with 4 nails, let's say, for example, has 2.6 kilonewtons of restraint, whereas when it has only 3 nails, has a lesser kilonewtons of restraint. So combined strutting counterbeams should be used to support roof loads and ceiling loads via hanging beams. They are usually located at right angles to hanging beams and parallel to ceiling joists, but may be angled or placed off centre. So it's our combined strutting counter beam. So it's strutting and it's also picking up a hanging beam. So it's going to be a very big beam. So our strutting beam here, minimum end dimension of 100 millimeters for the depth divided by 1/3, or depth divided by 3, whichever is the greater. So, yeah, if we don't have that, if we end up having to use a strutting beam, which is a much larger strutting beam, but then cutting that down so we have less than 1/3 of our depth in that, or less than 100 millimeters, then we have to think about other ways of strutting that route, providing several strutting beams and providing more struts through. Also, this is an important thing to note, 25 millimeter clearance at mid-span of strutting beam as well. Well, that's more for the chippies to work out. But the reason we provide that clearance is so strutting beams don't interact with our ceiling, with our roof space. Because if the ceiling is going directly on the underside of that strutting beam and we get some wind loads on that, it will bow the ceiling. And so we want to have that small accommodation for any flex in that strutting beam. So where the end dimension is less than 100 millimeters or 1/3 the beam depth, the average grade or alternative support method shall be provided similar to that shown for hanging beams. Underpellets shall be in single lengths where possible and in straight runs at right angles to the direction of the rafters. Where 2 or more rows of underpellets are required, they shall be spaced evenly between the ridge and the wall's top plates. Where underpellets joined in their length, the joint shall be made over a point of support with the joint half-lapped and nailed. So our half-lap is much as it sounds. It's your half-lap for timber. Alternative underpellets shall be lapped a minimum of 450 millimeters and spliced with either 6 through nails, so 6 nails through, or 3 number 14 type 17 screws, or 2 M10 bolts through the splice. Laps should be made over a support. So that's a fairly significant lap of 450 millimeters. Rafters may be bird's mouth to a depth not exceeding 1/3 of the rafter. So this is the bird's mouth of the rafter here. So that helps locate the rafter on top of that top plate, and you'll see that all the time with your rafters. A small accommodations cut out so they seat nicely on top of the top plates. They give an option here for a non-bird's mouth, so a wedge or framing anchor, but yeah, you typically don't see that.
Is that just purely a cost thing, or?
Yeah. I guess the framing anchor is very quick and easy, and I dare say actually if I look around, I'll probably see them with framing anchors certainly more than any of these wedges, but. I think producing cutting lots of wedges and having wedges in there is definitely a cost thing. That's expensive. Framing anchors not too expensive, but although also time consuming. If you're doing all your cuts for all your rafters, it's very quick and easy to go, okay, I'm cutting these rafters, I'm cutting them all to this exact length, and then you do all your bird's mounts at exactly the same spot like that. very quick and easy when you're cutting all your rafters to do that, and then they slot in space in a place, and then nail gun, like a couple skew nails, push, and they're set in place. Whereas with a framing anchor, you've got 3 to 4 nails at the end of each framing anchor. You've got to carry anchors around with you and put them in. So yeah, I imagine this is a much more preferable approach for carpenters. Roof strutting, so except as provided for clause, these various clauses, struts shall be either vertical or perpendicular to the rafters, or at an angle not exceeding 35 degrees to the vertical, as shown below. And they shall be bird's mouth or halved to underpurlins. So that's halved to that underpurlin there. So this angle here must not exceed 35 degrees. If we get more than 35 degrees, we get more than 35 degrees, well then the gravity loads are starting to rotate that strut as opposed to push through the strut. So vertical struts. And perpendicular struts. So that's struts that are perpendicular to the rafters. And or they call fan or flying struts. So equal angles not less than 45 degrees. So once this angle in here gets less than 45 degrees, there's too much pressure placed on that strut in an outward fashion from the roof load. Minimum angle to the horizontal 60 degrees. And then you've set the fan struts will have a 9 by 35 metre spreader cleat, both sides of struts fixed through an M12 bolt. Two type 14 type 17 screws. Once again, a chock to the fan strut. But the important points here are that they're equal angles and not less than 45 degrees. The perpendicular strut 60 degrees max, 45 degrees max. That's right. Collar ties should be provided in all coupled rooms. So where the rafter span is such as to require support from underpurlins, collar ties shall be fitted to opposing common rafters at a point immediately above the underpurlins. Collar ties up to 4200 long should be fixed to rafters with 3 75 by 0.35 machine driven nails. Collar ties that exceed that length. I'll flip through this fairly quickly because this is getting how to say, a little bit too in depth for our interests. So I'll try to comb through, find out the bits which are specific to the building designers and not call out as fixing sizes so much. So boxed eaves construction. So boxed eave construction enables you to when you're doing the span tables for your rafters, if you have to include an eaves span, that can make you use much larger rafters. So boxing your eaves, so tying it back with feet bearer, enables or cuts down the span of our eave here, which enables the use of smaller rafters. So these are details of that eaves construction, either as a box eave or your unboxed eave that has a hanger coming from your rafter to your seat bearer. Seat bearer that carries your eaves lining, so your 6mm fibre cement sheet, and typically you also have a quarter round dowel there for that gap between the brickwork and the fibre cement sheet. allows for shrinkage. Ceiling joists. Yeah, we've been through much of that. So, yeah. Important thing about cantilevers. So, for cantilevering, for example, gable ends or balconies or whatever, typically any cantilever is created by having 2 times the length of the cantilever as a back span to support. So you'll see that concept carry through with just about any timber framing member. The back span has to be twice the span of the cantilever. So, timber is a natural product drawn from the wood and the trunks of trees. Its character is consistent with the species of tree and the form and growth over time of the wood in it. So you can have the same species of tree grown in a different climate and get a different type of wood. In colder climates, typically they grow slower. Warmer climates, they grow much quicker. New wood grows on the outside. The oldest wood is on the inside. The diameter is largest at the base, and 1 ring or layer is per growing season. So trees in the forest grow towards the light. So in densely packed forest, the tree trunk is straight. The lower branches die, leaving small knots in the wood. The bark protects the wood from damage. The trees shed their bark each year. So as you cut into a tree, you'll encounter these layers. They're not always so evident. In some species they are, some they aren't. So we have the outer bark, which is shed. We have the inner bark. We have the cambium layer. We have the sapwood. So this is our sapwood here, our lighter coloured wood, and then the heartwood in after that. So has anybody ever chopped into a tree and seen those various different layers in a tree? Yeah. Typically the sapwood stands out. It's a lighter colour piece of wood. It's softer on the outside there. And we need to know about that because at times we need to distinguish between the use, well, sapwood doesn't have the same strength as the heartwood, so it doesn't have the same stress gradient. So pith is the start of the growth of the tree in the original sapling, so this is our pith in the centre. Cambium has the growth cells, so the wood cells created on the inside, bark cells created on the outside. The sapwood, it's this one here, is the newest wood on the outside of the tree, takes nutrients from the roots to the leaves. And the heartwood, the older wood, this one in here, the cells are closed, can't pass nutrients, and it's a repository for waste and extractives, etc. for the tree. But it provides structure to the tree. That's the main thing. With the classification of hardwoods and softwoods, it gets a little bit funny. Not all hardwoods are really hard, and not all softwoods are really soft. A fairly notable exception to that is balsa wood. So balsa wood, does anybody know balsa wood? You've seen that for modelling and using that. That's actually a hardwood. So it's a very light timber. It's actually very soft. You can press your fingernails into it. But they're classified as hardwoods and softwoods not so much by their characteristics, but by the way in which they grow. So softwoods have regular cells, whereas hardwoods have these vessels within within that have cells packed around. So these intermediate vessels in them, and that's the difference between the structure of the two, and that's the difference between the classification as well between hardwood and softwood. So things that vary the speed of growth of trees. So the species and the genetics, the climate, whether it's wet or cold, or wet or dry, cold or warm. You'll see that in central. If any of you guys travel into Central Australia, the trees there are incredibly slow growing, but really very hard woods. Whereas typically in colder, wet climates, Mount Gambier, for example, where a lot of forestry is carried out, you get very fast growing trees with softer woods. Interesting thing, I was in Iceland and visited a cemetery in Iceland, just out of interest. And there they plant or it's quite common to plant a tree on a grave. And you see these graves, it's got 1930 marked on the gravestone or so, and it has a tree about this tall on it. Being a very cold place that doesn't receive a lot of sun throughout winter, the trees there just grow really slowly, and so that's an example of where you get these cold climates that the trees grow incredibly slowly. It's also because of the poor soils there as well. Also, the arrangement of the tree will dictate how it will grow, whether it's native forest or plantation. So each piece of timber is unique. So that's a piece. Oh, what is that a piece of? It might be a piece of fairly new jarrah. I'm not so sure. It's fairly pink. It looks sort of like Tassie oak, but it's a bit pinker than Tassie oak. I'm not quite sure that one, but yeah, quarter sawn hardwood. And this one is a myrtle burr veneer. So the myrtle is a tree, and the myrtle gets these large lumps on it called burrs. I think it happens because of an insect or something. They get these large lumps on them, and then timber producers get those lumps and take fine shavings off them for use in veneer, because they've got this real feature to them, because they're this fairly knotted consistency. Properties of variable. Dry, seasoning and shrinkage, strength and hardness, durability and appearance. So some timbers are chosen for their durability, some are chosen for their appearance. So when we've got our growing tree, the cells are completely saturated with moisture like this. Then we chop it down, and it sits there for a couple of days. We have partially seasoned timber, so we still have sort of 25% moisture content there. But then we season the timber, be that in a kiln or over time outside and covered, and we don't fully remove. We remove down to about 10% or so moisture content of that timber. The drying timber increases its strength, stiffness, stability, and durability, and its ease of fastening. The thing with the fastening is that if you fasten into unseasoned timber, later on when that timber loses its moisture content and shrinks, it no longer binds to the nail to the same extent. And so you can have a loose fastening if you're using unseasoned timber. Yeah, so ideally it is dried to a moisture content in equilibrium with its service environment. Timber shrinks at different rates in different directions. Once dry, it will expand and contract to maintain equilibrium with changing local conditions. And that is why for example, whenever a deck is specified or put down, you don't lay timber right next to each other. You maintain that 5mm gap between all your boards, because hardwoods particularly expand and contract with moisture. But they expand and contract not in an equal fashion. So some of the expansion and contraction happens in a radial fashion, so that's across your growth rings, in a tangential fashion, which is along the growth rings, or in a longitudinal direction, which is along the grain of the timber. And your different types of woods have their different, how do I say it? They react differently to moisture. So radiator pine, when it's going from 12% to 25%, will have 3.5% radial shrinkage and 4% tangential shrinkage. Let's put out Kauri has a radial shrinkage or expansion of 4.5% and tangential of 10%. So the tangential shrinkage being double the radial shrinkage, when that dries out, it'll bow. So with this piece of timber here, when that dries out and loses moisture, it's going to pull in here like that, and it's going to bow in that fashion like that as it dries out, or conversely, as it takes moisture in, it's going to cut in this fashion, because the tangential shrinkage is far more than the radial shrinkage. And you can see from this table, your percentages are much higher for hardwoods than they are for softwoods as well. So we have to be more careful with expansion and contraction due to moisture with hardwoods than we do for softwoods. But tangential shrinkage is typically the highest, so growth rings tend to shorten as the timber dries. So here's an example of what's going to happen to those cross sections of timber as they dry out. So showing where they're cut from the log. You'll see this one here is the most stable in its, so it's not cupping or bowing significantly. So it's most stable. That's what's called a quarter sawn piece of timber. Pines have a porous cell structure. They can be dried very quickly. Turnaround time from saw to stalk can be as low as a week. Hardwoods have a non-porous cell structure. The moisture must diffuse through the cell wall. Drying can be very slow, and it has to be done very carefully. Because if it's not done carefully, if we've got this differential shrinkage, you get cracking in the timber, which is not desirable. A bit about strength of timber. So timber is very strong and stiff when parallel to the grain, but weak when perpendicular to the grain. So anybody who chops wood for firewood would know that you don't get a log, place it on its side and try to chop through that way. You tip it up and you split it. Timber is a natural material. Each piece is unique in fibre, texture and colour. Its strength is dependent on the properties of the wood and the slope of the grain. It takes up and gives up moisture, expands and shrinks as it does so, and deteriorates in line with exposure. Timber is available in a wide range of products and species, including solid sawn, moulded and laminated timber, veneer, plywood, and wood panels. Hardwood or softwood, solid timber cut from a logged and dried. It's a versatile material used for moulding frames and exposed structure. Size is restricted for your sawn members, so you're restricted to 6 metre lengths for your softwoods. Timber products can be either hardwood or softwood. solid seasoned timber milled to a wide variety of shapes. Glue laminated timber. Has anybody ever seen a glue laminated? Well, you've probably seen a glue laminated cutting board. Almost everybody would have seen a glue laminated cutting board, but bench tops as well sometimes, or as feature beams in houses as well. So that's a form of an engineered beam. But typically when you use an engineered beam in a house that's going to be exposed, we use these glue laminated beams because they're more attractive than your standard LVLs. So there's a example of glue laminated bench top. The veneer. So thin layers of solid wood are sliced from a flitch or peeled from a log and dried. The high quality material is used as a decorative finish. So they find pieces of timber that have a high feature grade, like a desirable grain or so in the timber. Lower grade material is also used to make plywood, LVL and similar products. So any musicians here that play guitars or timber instruments? Cool. Or if you have a good look, often fantastic timbers are used for your more expensive guitars in that veneer sense. You get some very interesting timbers used for finishes of guitars. Also, with your older cars, not so much the modern ones, but your old English cars with a walnut veneer for their dashboards and things like that, and in various different furnitures. Actually, yeah, I guess IKEA furniture is a large user of veneer as well. They don't select sort of the high grade timbers or high feature grade timbers for their veneers, but yes, they also use veneer. But layers of veneer glued together so that the grain, so this is plywood, layers of veneer glued together so the grain direction alternates between layers. So we have grain going this way, grain going that way, etc., etc. So usually produces sheets. Very good in a structure as a lining and flooring surface. Also typically used for hoarding around building sites. Or can use it as bracing panel. Other wood panels made from wood or wood fibres bound together with glue or other binder. So medium density fibre board. Some issues with MDF in breathing the fibres when cutting it, because you get very fine fibres with that. But it's used in a lot of applications. Particle board, hardboard, and core board. The appearance grading is the process of sorting products into groups with similar characteristics and properties. The timber is identified by calling up a specific grade. The most commercially available timber in Australia is graded to AS 1810 for timber seasoned cypress pine, 2796 for hardwood, sawn and milled products, and 4785 for softwood, sawn and milled products. The standard defines the requirement for hardwood. It is used for visual applications, accidental flooring, lining, and cladding. So that's 2796. It is in two main sections: product requirements and visual grades. Establishes permissible limits on gum veins. So gum veins, if anybody's worked with Jarrah, you'd know about gum veins. Does anybody know what a gum vein is? I'll try to draw one. So, if you've seen, does anybody know what the timber Jarrah is? Seen that? A few people have seen that. So very hard wood from Western Australia. So this is our piece of Jarrah like that. Typically, and you want to find nice pieces if you can without any gum veins. But sometimes you find these, like a dark section that will go, you know, a bit, like quite often they're on a curve like that, and there's a little piece missing, and there's all these little bits of sappy sort of stuff in the timber. That's what's called the gum vein. And yeah, in those hardwoods, particularly like jarrah, it provides no structural support in that area. So you have to be aware of such things. If we've got a beam running like this, and we have a great load happening there, and we've got this gum vein which sort of happens in this fashion like that, that's taking a decent amount out of the timber, we won't use it for that application. So you have to look for those specific things. Knot size and frequency. Not all knots are the same. In timber you've got dead knots and live knots. Can anybody think of when they've seen or can you think of what a dead knot looks like or a live knot looks like in a piece of timber? Has anybody ever seen a piece of timber that's got a knot in it and you can push it out with your finger? That one's a dead knot. So that's when a branch is dead in a tree and the tree is cut down, that little piece of timber in there will end up being a dead knot, which is not bound to the timber. If that branch is still alive, coming out of the timber when the tree is cut down, you'll get a knot in there, but that knot will be bound to the rest of the timber. You won't be able to push it out. It'll, be a scenario that looks like this. You've got your piece of timber, then you've got your various different grains, and then you've got a thing happening there like that, and then a bit of a thing there like that. That's your live knot. Your dead knot will have a much darker ring around it. Might be quite dark itself, and it's loose in there. Splits, cracks, and checks. So not so common in your softwoods, but very common in your hardwoods. Graded for stain colour, grain, uniformity, and its utility. It's want, wane, cut, bow, string, and twist. Now, do I have all those on the next slide? No, I don't. Has anybody heard of waney edged boards? Bit of a thing on grand designs in England. I think I saw a few. It's very, how do I say it? It's using just naturally sawn timber, so we get a natural log and we slice straight through it to make boards for the external cladding of a house. And we'll end up having a board which is sawn on the top like that, but then the bottom will be a bit like this. Anybody seen that sort of thing? And then your next board goes over top of that. It's all a bit sort of arts and crafts, oldie-woldy. That's what's called a waney edged board. And so that, basically your want and your wane are the same thing. So a piece of timber which is a missing, so the rest of our timber is nice and straight. Let's say, nice straight piece of timber. That we call is the want or the wane in a piece of timber. If we've got a piece of timber doing this, that's cupping. Opposite is bowing. Spring, so we've got timber doing this. And twist, or also referred to as propeller, is where you've got, it's a bit hard to draw actually. So here's timber which has a longitudinal twist in it. So grade range from select grade uniform wood with few natural features through to high feature grade, including lively natural feature as part of the desirable aesthetic. tolerances are established for major product groups, like grades, so joinery, dressed boards, strip overlay flooring, etc., light decking, ironing boards, things. So, oh, there we go. Bow and spring, twist and cut. Oh, so sorry, with my diagram, I got bow wrong. So bow is end to end bowing, as opposed to bowing in a tangential fashion. So for our hardwood classification, no sapwoods that are susceptible to lictids are allowed, so small wood-eating insects. Moisture content anywhere in a piece must be between 9 and 14% for most products, including flooring, 8 to 13% for parquet and furniture components. So slightly lower moisture content for the timber that's going to be used inside where you don't want any shrinkage happening. So with the hardwood, standard recognises features as a desirable visual characteristic. Therefore, distortion and machining tolerances are associated with the product and not the grade. The timber can be specified with desired appearance for any function. I'll flick through this a bit quicker. Timber is a highly versatile material that can be shaped and joined easily. So this is what's called a housed joint. This is a half-housed joint, and this is mortise and tenon. So mortise is your bit, your gap in here, your hole, and tenon is the bit that goes in. A good way to remember that is a carpenter will have a piece of machinery called a mortiser. So a tool for creating a square mortise. Other joints, a biscuit joint, typically used in furniture, or dowel joints also used in furniture. We don't really use those in building at all. Overlap, very common in building, and fixing blocks, sometimes used in building. Making timber durable. So this one's fairly important for the assignment. Durable means the capacity to perform satisfactorily for a specified period. Stress grade indicates performance when it's new. Durability indicates how the level of performance is maintained when the timber is old. Can anybody think what the difference between your overall, or let's say, durability and natural durability is? What the difference between those two things are? So your durability, that relates to how long a piece of timber, or how durable a piece of timber is when it's treated. Well, not necessarily, it may be in its natural form, but durability is the overriding classification for how we can use a piece of timber and how it's got to withstand certain elements and exposure. And that may be treated or untreated, whereas natural durability is just about the species of timber and how it naturally performs without any treatment on it. So here we've got 500-year-old recycled timber used in a scenario, or we've got a thing over that, but a 700-year-old barn with large oak trusses. The elements in the natural environment can degrade timber, decay, etc. Damp and microorganisms cause rot. Insect damage such as termites and borers. Weathering damage such as cyclic wetting and drying. And ultraviolet light cause discoloration and cracking. The maintenance ensures protection remains functional. So we maintain against physical hazards and biological hazards. Design minimises exposure to hazards. So we can design in a way that makes it very difficult for difficult for termites to get to the timber, or we can design in a way to ensure that the timber is not exposed to those physical hazards. And we can choose types of timber that will be resistant to either those physical hazards or the biological hazards. The way we choose those timbers, different types of timbers have their different durability gradings, and you can buy timber, like a specific type of timber which has a specific type of treatment, which will have its durability grade at either H1, H2, H3, H4, H5, or H6. So a typical piece of timber that you will specify in a house frame are your fascias. Fascias, they see a lot of weather, they see a lot of rain, but they're up from the ground. So the timber you specify for your fascia is H3. And the way we achieve an H3 piece of timber is typically with LOSP, so light organic solvent protected pine. So yeah, you'll see that for your verandas, for your pergolas, for fascias, etc. H3 LOSP treated timber. H1 hazard class can be used inside and above ground and exposed to insects, only to insects other than termites. So H1 treated can still be eaten by termites. H2 inside and above ground, exposure to moderate decay, borers and to termites. H3 outside and above ground, moderate decay, borers and termites. H4 outside in ground, so it can withstand severe decay, borers and termites. H5 outside in ground or fresh water, so for jetty ponds and things like that in the freshwater setting, very severe decay, borers and termites. And H6 timber, or hazard class 6 timber, can withstand marine water, so marine wood borers and decay. So you've got some natural timbers that stand up very well to that scenario, like all your jetty piles made out of turpentine, that Australian hardwood. So naturally they meet that hazard class. Hazard class 1 applies to framing, flooring, furniture, and interior joinery, but only where timber being used is exposed to attacks from insects other than termites. H2 also applies to framing, flooring, etc., but is resistant to termites. So H3 applies to weatherboards, fascia, window joinery, exterior framing, and decking. H4 applies to fencing, greenhouses, pergolas, and landscaping timbers. H5 applies to retaining walls, house stumps, building poles, cooling tower fill. Don't know what cooling tower fill is, etc. H6 applies to marine piles, jetties, jetty cross bracing, landing steps, boat hulls. For low hazard environments, non-durable timbers are okay. So intermediate to high hazard environments use timber species that are naturally durable and or timbers that have been treated chemically to improve natural durability and or design the building to protect the timber from the environment. All timbers in Australia can be classified according to their natural durability for both in-ground and above-ground applications. So class 1, turpentine, the most durable. So this is not your hazard classing. This is your classification of durability of timber. So turpentine is your most durable, through to radiated pine, untreated is the least durable. So this is what we're typically building with, radiated pine, unless we're building a jetty. Timber can be treated chemically to improve durability. Chemicals act as a fungicide and or insecticide. What you should not do is use H3 LOSP timber inside a house. Because it off gases over time, it's not allowed to be used inside a house. So it's only for external applications. Chemicals only absorb into the outer layer of the timber, so care must be taken to patch or protect cut ends in areas of concern. If you are concerned about use of, let's say LOSP or other timber preservatives, you can use a stain sealer on the outside of timber to lock that preservative in, and likewise treat your end cuts as well with that stain sealer. Levels of chemical treatment vary to suit levels of hazard, e.g. H1 to H6. Such timbers are branded to assist choosing a timber to suit the environment. And this is an important one for you. So the durability of timber can be improved by designing the building to help protect the timber. So use claddings, roofs, replaceable cappings, paint systems and sloping surfaces. Ensure timber posts are elevated above water, so by using post brackets, and detail connections to avoid water entrapment in joints. Ensure subfloor construction incorporates an inspection zone to detect termite attack and allows appropriate levels of ventilation. So protect timber from water, so end capping or end grain capping. It's also about how you cut the ends of the timber. Say in this pergola here, we've got a small straight cut and then a sloping cut of some sort to help drain water away. If we, and you may have seen it before with pergolas that haven't been finished nicely, where you just have a piece of timber, let's say our rafter goes like that. Or actually, let's put a little bit of slope in our rafter, probably the best. Put a slight amount of slope in our rafter, to our pergola, and it just finishes like that. You get water, of course, running down the rafter or tracking down the rafter, and it sits there. And when enough of it sits there, you get a drip. But when you don't get enough for a drip, it sits there continuously and then soaks in the timber, and you'll end up getting a rotted portion to the end of your timber. Has anybody seen that before? Yeah, so a poorly constructed or poorly thought out pergola will have that, and that's why you typically see this detail there. And that detail may be this type of end, or it might be that, or it might be, let's say, the other one, really long slope. Various ways of doing it, but it's to ensure that your drips drip off the end better. Give timber good ventilation and avoid condensation. So sometimes condensation can be very hard to avoid. Although ways to avoid condensation, or plasterboard certainly helps with condensation a lot because it takes up the ambient moisture of the house and sort of works as a sort of moisture flywheel. But also insulation in your house as well. If you insulate well, you don't. You always where you insulate poorly is where you get condensation. And unfortunately, that happens on windows here as well, because of course you can't insulate the window. You get moisture build up on the inside. As the outside of the window pane is cold, the inside is warm. So that's in regards to durability. final set for timber is termites. So, a managed approach is best. There are more than 350 species of termites, but only 20 cause economic damage to houses. All 20 attack houses from underground. The emphasis of current building regulations is on managing termites through barrier systems and inspections rather than employing environmentally harmful methods. So, example of that is DDT. A CSIRO study found that steel and masonry houses had virtually the same chances of attack as timber houses. Termites can also cause damage to plasterboard, carpets, plastics, books, artworks, clothes, electrical insulation, and fit-out timbers. The potential risk of attack also varies according to the location of the house in Australia and site-specific features of the local environment. These sites need special attention. The key priority is to provide a system that addresses the whole of the house, not just the structural elements. This usually consists of a barrier system built into the construction that is designed to assist termite inspections once the house is occupied. Termite barriers are inspection systems to stop hidden entry. They are not prevention. Systems stopping termites actually getting into the house. Regular inspections use the barriers to look for termite entry at predetermined locations. Termite activity can then be controlled. So all of you probably would have seen ant caps on the top of stumps before. That forces the termites to build a mud nest around that ant cap to get into the house, which makes them visible. So, concrete slab is a solid unit constructed to prevent termite penetration. However, with a concrete slab, where they do still get through is at all your pipe locations. So let's say we've put a pipe through for the bathroom and cast the slab. As the slab sets, it shrinks slightly and shrinks away from that pipe a little bit, and you get a couple millimetre gap between your pipe and the concrete, and the termites can come up through that and then into the house. And that's the way that the termi mesh is used. So you use a bit of termi mesh around the pipe with a hose clamp that gets set into the concrete, and so it closes up that gap or stops that gap being able to be for the termites to penetrate that. Crushed stone, so a layer of stone particles too hard and heavy for termites to penetrate, can be a way to stop termites. So that's one product called granite guard. So it's just lots of crushed granite underneath the slab. Sheet capping, so sheet material used as an isolated or continuous subfloor barrier. So an example of it being an isolated barrier would be an ant cap, like that on the top of the pole. I haven't seen metal sheet used as a continuous subfloor barrier. No, but I can imagine it. So on top of the strip footing, you have just a continuous piece of metal sheeting that would be bent over. Stainless steel termite-proof mesh used as an isolated or continuous barrier. Or chemicals, periodic application of chemicals around under buildings to repel or kill termites. So red, sort of pink shading in diagrams indicates termite barrier locations. So under your stumps, stone or chemical may be used around footings as an alternative approach, and then ant caps on the top. With the slab, extra detailing of joints and penetrations using mesh, caps or stone. Oh, that's another one. 75mm exposed edge of slab all round. So you can design your house with 75mm edge of slab all round, but then your clients might put paving down or something like that. and that can then, if you carrying your paving up to the height of your slab or beyond the height of your damp course is bad for several reasons. One is that you end up sending moisture into your house if you've got any slope towards that, but then also it's a place for termites to just go very easily into your house, to eat the house as well. So more examples of common barriers, so slab on ground. Extra detailing at all edges, mesh caps or stone in the wall, chemicals or stone in the soil. Slab on ground with septic barrier. Can't get that back. So that septic barrier may be, what have we got? Cordon. There's a product called Cordon, which is a vapor-proof membrane sandwiched with a piece of fabric in there that's got termiticide in that fabric, and then another layer of the vapor-proof membrane. That's set down under the house to work as a vapor-proof membrane, but it's also will also kill termites that try to cut through it as well. Yeah, whatever barrier system has been used, its effectiveness depends entirely on regular inspections by the building owner. No termite management system works properly without inspection. So AS 3660 indicates that inspections be conducted at intervals of not more than 12 months. More frequent inspections are recommended strongly. Enclosed subfloors also require an access door to facilitate inspection. Large and established sources of termite food and nesting near the site, either bushland, increases the likelihood of termites. Permanently damp ground increases the ability of termites to attack, i.e. they can more readily build mud tunnels from the ground. I had an issue myself with the delivery of a whole heap of hardwood timber to a site, went straight on the ground, it didn't go on bearers. I didn't get there for another 2 weeks after it was delivered, broke it apart and had termites starting to eat the face of the timber already. So that's within 2 weeks being on, yes, the timber was getting wet, sitting on a wet ground, but yeah, within that short period of time, get termites into the wood. So it can happen very quickly, especially in the presence of moisture on the ground. So, the thing to do there would have been to deliver the timber on bearers, have it stack on bearers, and also stack it in a fashion with some bearers in between to let that air pass through it. But fortunately, it didn't do a great deal of damage. It only just started on some stuff, so it was easy enough to deal with. The further north in Australia, the greater the prevalence of termites. When building right up to boundary, inspections may not be possible from the neighbour's property, thus increasing the risk of hidden attack. When adding house extensions, the risk of attack can be increased by problems such as a lack of barrier continuity, subfloor ventilation, and subfloor access. High-risk sites require additional consideration to the previous methods, e.g. use treated timber, prescribe inspections at closer intervals, consider getting specialist advice. So that's it for timber. Do you feel that? Well, I guess it's been quite a sprint to the finish. But do you feel that do you have any questions or any areas in regards to timber framing that you feel a little bit lacking still, or anything?
Something that's always worried me with that timber code.
Yeah.
So they show, like, you look up decking and things like that.
Yeah.
Of what timbers to use, and they'll always have two, because it's like treated pine's fairly soft. It's not,
Yes.
not
Yeah.
like hardwood, but then, I've had someone say, you can't put them together like that, they'll just rot out. Even if they're treated pine.
Yes.
They'll never dry around them. It'll always like if there's not a roof over it,
Yeah.
over the decking,
Yeah.
the water will get in there.
Yes, get in that gap.
And it won't get out.
Yeah. Yeah.
So, but they don't put in there like put spaces there when you bolt together and all that. So
Yeah. So that's an area that's more. Well, that's something more for the designer to think about. So if you're the designer, specify now that the span tables will say to achieve this span, you can use two 120 by 35s. That will so two 120 35s now laminated together will achieve a certain span. And as the designer, you have to go, well, actually, that's not a very good detail for use outside. Can we instead use a larger piece of timber, or should we instead spend the extra money and go for a hardwood? Or, well, certainly we use LOSP, treated timber, in that scenario anyhow, being outside. But yeah, that's sort of where it comes down to the designer thinking, okay, well, yes, the span tables enable the nail lamination of timber, but is it actually a good use or good application of it?
and if you decide to put an LVL, then
You can't.
very good outside.
No, you can't use an LVL. Yeah. No. So it has to. So it's either that option or it's the expensive option, or it's the option of more supports. Yeah. And depending on how much money your client wants to spend on the deck and how much longevity they want out of that deck, it's that trade-off. Yeah, I think certainly the best scenario is to, well, it's probably much better scenario is to have the phone number of plenty of, or there are plenty of recycled timber places around as well that a lot of them know very well what's in their yards, and you can go, what do you have in a hardwood that will span, do you have any jarrah that's sort of 130/65, something like that, will get a large span for under a deck, and that can often be a really cheap way of going about it as well to get your hardwoods, because buying your hardwoods new is incredibly expensive, and for large sections it's very expensive, but second hand, quite often you can get this you're after as well. So,
No,
but,
right.
yeah. But no, that's a
Sort of, I don't know. They say you can do it, so it's
Yeah.
probably right. But
yeah.
the other option's a steel beam, I suppose. Then you've got an engineer to come in and
Yes.
design a beam, then
Yeah.
it costs more again.
Yeah, certainly, and that's, although some of your steel suppliers for simple calculations like that will do that to sell a beam as well. So you can say, look, I need a beam to span this much with this load on it. Are you able to do calcs for me for that purchasing through you as well? That's an option, but yeah. So I guess the timber framing code, the span tables don't make all the decisions for you in regards to where you use nail laminated timbers. And that has to come down to design. That's a really good point. Any other questions or things, or aspects of houses you think we should have covered in the timber framing portion?
Sure.
Yeah, actually, I think we probably could have gone more into trusses. I'll see if further down. Yeah, we don't. You know what? I reckon we could have covered trusses a bit better. We only just briefly touched on trusses for that. We'll press on because we've got to do. We'll have a look at. We'll have a look at steel framing, and there's a bit to do with trusses in steel framing, and we'll push on with concrete and cladding systems. But if you guys are interested, I probably wouldn't mind revisiting or visiting trusses at some point in time as well, and going through that. So I'll see if I can gather some information for truss roofs as well for that. But yeah, once again, thank you for your attendance and your attention. Particularly tonight's lecture does get a little bit dry, particularly with the timber, with the span tables and the